So this is a team from Florida Institute of Technology, Vincent Andrews, Emily Happy, and Emma Sandidge, who competed, although we don't like that word compete, they accepted the challenge, and they'll tell you all about it in our recent SCUDEM that was held this fall. They were one of 20 plus teams that were outstanding, and their video is online at the Simeode YouTube site for complete viewing. What we've asked them to do is talk about what this meant to them, how they did it, and details. And so I'll turn it over to Vincent, Emily, and Emma.
All right, and do you hear us okay?
Yes, I can.
All right, so I'm Vincent Andrews, and I'm here today with
Emily Happy and Emma Sandidge. And again, we're a team from Florida Tech, and we're going to be sharing our experience competing in SCUDEM along with the presentation we submitted for judging. So first of all, we wanted to talk a little bit about what SCUDEM is and how we participated. So SCUDEM is a global challenge hosted by Simeode for modeling differential equations outside of the classroom. Teams of 3 students get 3 weeks to post a 10-minute video modeling one of 3 problems that comes from the either life, social, or physical sciences. And then after uploading their video, there's around 8 judges that provide feedback and then rank student responses, either successful, meritorious, or outstanding. And then from here, we are going to present our model as we submitted it to the judges, and we'll follow up with some feedback and further applications.
All right, so just our little introduction. So in this presentation, we're going to define the problem, explain the assumptions that we created and some that were given to us, create our model based off these assumptions, and attempt to solve it, and then describe some limitations and further applications of our model. So the problem outline that we were given, our goal was to develop a model to mimic the jaw movement of the Actinopterygian fish that pulls water and prey into its mouth for feeding. Some background on these fish is that this class of fish make up over 50% of living vertebrate species and contain fish such as pufferfish, lionfish, eels, and largemouth bass, which we talk about specifically later. So from here on out, we will develop a mathematical model of jaw movement, estimate the minimum time it takes for the mouth to open and close, and explore the effectiveness and a range of this feeding technique.
So before we began our model, we knew that we had to make some assumptions first to best fit our model and apply some other conditions that were given to us in our problem outline. So the first thing that we noted was that the mouth parts have simple attachment points at their ends when the jaw is fully extended. And this allowed us to proceed with the model that we're going to explain in the next few slides. We also noted that the fluid interactions do not affect the motion of the jaw, and this was something that was noted in the problem. They wanted us to consider the force of the jaw without any influence from the fluid itself. And so we did that with our model. And then another thing we mentioned was that this was a 2-dimensional system because we're only considering the fish, the predator moving towards the prey in 2 dimensions and not moving in any Z direction or side to side. And then we also note that the active muscle region subjects is limited to certain regions of the jaw. And this was something that we got from our research from the paper that was provided on the morphology of the Actinopterygian fish. Another note that we had was that the amount of prey is constant and they are all the same size. And we thought this was important to include because the fish or the predator needs to be tracking fish that are of approximately a consumable size for how big the prey is. And we also noted that the amount could be plural if the fish was consuming lots of tiny fish. So including going off of the fact that the mouth parts have simple attachment points, we assume that the motion of the jaw can be modeled periodically using simple harmonic motion. And then a final point we had here was that the buoyant force and gravity cancel out. So the only thing affecting the y direction movement of the fish was the opening of the jaw. And so here we have an image that we extracted from the document provided on the morphology of Actinopterygian fish. And on the left here, it shows a largemouth bass fish, which is what we use to complete our model. And then on the right here, I have highlighted the major components of the jaw that we're going to be looking at. So we have the lower jaw in blue, the pectoral girdle, the composite hyoid, the premaxilla and the maxilla. And so these are the parts of the jaw that are having the most effect on the force for the suction feeding technique. And so these are the parts that we thought would be best focused on. We also noted down here that the force would be maximized at these fixed endpoints that we mentioned of the jaw, when the highest vertical displacement is at the y maximum, and the time that this would be t max over tail. And so now we're going to go more into our model here.
So our function will model the vertical displacement of the jaw, meaning how much it's open with respect to time. And we pictured the fish's mouth opening and closing similarly to a periodic function. And because the mouth parts were assumed to have simple attachment points, we utilized simple harmonic motion to fit our model. And the following differential equation is modeled below, along with the constraints that the muscle forces are positive, the mass is positive, and the time begins at 0. We also noted an initial condition that our function is 0 at t equals 0. This is because initially the predator's mouth will be closed. And below we also have our variable declarations used in the equation. So m will be the mass of the predator. Beta is our damping force, which in this case we decided was due to water resistance. Y of t, our function, measures the vertical displacement. And K1 through K5 are the respective forces that correspond to the muscles found in the fish.
So we had a couple of structural limitations as we were creating this model. So the feeding technique is based on the reaction time of both the prey and the predator. So if the predator must be faster than the prey in order to be successful in feeding, the prey cannot have a faster reaction time. Then it takes the time for the predator to fully open and close its mouth, or else the prey will escape. And the predator must also be in very close range to the prey, or if the predator has to have an extremely strong suction force to bring the prey into its mouth from far away. And the prey must be smaller than the width of the predator's jaw when it's fully open and closed, or else the predator will not be able to feed on the prey.
So now we're going to talk a little bit about a simplified solution that we found for our equation. So in reality, the muscle forces of the jaw will not be constant throughout the process of the mouth opening and closing. This makes sense because as it opens and closes, there's different amounts of force being applied in different areas. But when they are variables, the differential equation becomes much more complex to solve. And we just wanted to visualize a simplified version of the equation. So we assumed that the damping force, meaning beta, is equal to 0, and the muscle forces were constant. So our condensed equation is as follows, and we have summed all the constants into the capital K to represent the muscle forces. And since we are allowing each muscle force to be constant, it makes sense that we can group them all together into another coefficient. So again, we keep forces, mass and time constant, along with the initial condition that at time equal to 0, the vertical displacement is 0, meaning the fish's mouth is closed. And to continue this solution of the differential equation, we have now condensed our model into a second order linear differential equation that can be solved using the shown characteristic equation. So we get mu squared is equal to negative k over m, and this shows that the roots of the function will be complex valued. And due to this, the appropriate choice of solution are sine and cosine functions, which we have shown below, with the value of mu inside with t. And then we also applied our initial condition, meaning C2 must be 0, because when you apply times 0, cosine of 0 is 1, and we need that term to disappear in order to satisfy our requirements. So therefore, our final general solution is given below. Then we wanted to move forward into solving for t to get a sort of estimate of the time it takes for the fish's mouth to open and close. And to do this, we applied the attributes of the sine function to find this value. And so the longest time the mouth will be open corresponds to when the argument of sine equals pi over 2, as that is when that function is maximized. So doing that, we get the value that t equals pi over 2 times the square root of m over k. And then to get the total time for the mouth to open and close, we multiply this value by 2, giving the max time to be pi times the square root of m over k. And the shortest time frame for the mouth to open and close will be less than the t max value, but it also must be greater than the reaction time of the fish if the feeding method is to be successful, meaning that the fish cannot react quickly and escape before the predator's mouth is closed.
So after we completed our model, we decided to further analyze the damping force present situation. And so we rewrite our differential equation considering the damping force as beta, and we said this was due to the water resistance in the scenario. So then our differential equation becomes what we have below there, and we can rewrite this using the angular frequency for harmonic motion, where omega n squared equals k over m. And then we can rewrite the equation of motion as the following expression, where zeta is our damping frequency. And performing some further analysis, we noted that the system is undergoing a critical damping force since the mouth immediately opens and then closes. It's not undergoing consistent oscillatory motion like a spring or a guitar string, for example. It's immediately opening and returning back to that ground state when t equals 0 and the mouth is closed. So zeta here would be equal to 1 for the critical damped case. And this ends our presentation as we originally submitted it. So now we're going to go into more talk about our developments.
So after we submitted, we got a lot of feedback from the judges. And so in the next couple of slides, we will talk about some adjustments and clarifications that were made based on those comments and questions we got. So we were asked why simple harmonic motion was used. And we chose it because we wanted an equation that we might be able to provide a solution for. And with simple harmonic motion, we could get a solution in sine and cosine, which we thought would model it the best. In a few slides, you'll see our new work on this. But yeah, so we chose simple harmonic motion because the jaw immediately opens and closes, and the damping force acts in opposite direction with the motion, the jaw opening. We also only consider motion in the y direction because the force of the jaw only moves in the y direction, and the predator or the prey would be moving towards the mouth in the x direction. So we chose a 2D model. We didn't want to model the motion of the jaw opening in the z direction, which in reality, the mouth would also open side to side. But in order to provide a simple solution, we only considered it in 2 dimensions. Creating a 3D model could be in the future direction of this problem though. And we were also asked to explicitly state the questions from the problem page and then the answers to the questions. So one question, where and when were the forces acting on the mouth the strongest? So we said at the fixed endpoints of the jaw and when the mouth is fully open. Some potential limitations of the structure would be the reaction time of the prey must be greater than the reaction time of the predator. Prey must be in close range, and the prey must be smaller than the jaw of the predator at its widest. And also be effective. The only question we did not explicitly answer before was one about the effective range of suction feeding. So we said that the prey must be close, not knowing the flow rate of the water into the predator's mouth. If we knew the flow rate, we might be able to actually calculate a time and the distance the prey must be from the predator, depending on how strong the suction force was. But we weren't provided with that, so we were not able to get an exact answer.
So for improving our model, we decided to focus on a few main points that we thought were most important or things that we think need to be changed about our model. So one thing that we did notice was that the mass of the jaw the mass should be the mass of the jaw, not the entire fish itself, since the mass of the jaw is the thing that's undergoing oscillatory motion, not the entire fish. The second thing we noticed was that the damping force is not from the water resistance, but we can actually express this force as the force of the jaw is retracting in the opposite direction of motion. And this just comes from the original definition of what damping force is. It moves in the opposite of the direction of motion, which in this case is y. So we can express that as beta equals negative ky, where k is some constant for the motion. And the last point we had here is that the jaw is initially closed and there's no force in the jaw opening at t equals 0. Therefore, we gain the following condition of where y of 0 equals 0. And in the next couple of slides, we're going to go more into developing our model into to fit the critical damping case for harmonic motion, which is a special case. Therefore, we get a slightly different model as you'll see.
Yeah, so like Vincent said, now we're going to show some modifications we made to our differential equation after we received some of the judges' feedback that highlighted the fact that we did assume the damping force to be 0 to get our simplified solution. So in looking at this again, we wanted to more accurately represent the phenomenon. So we decided that this damping force would be a variable and not equal to 0. So below is our new equation where our damping force is shown by B, and again, it's equal to negative ky, where k is the spring constant of the system. And again, the system is critically damped, which is a special case of simple harmonic motion. And we kept our variable declarations basically the same. The only thing, again, as Vincent said, we adjusted that m is the mass of the jaw and not the entire predator to be more accurate. So the definition of critically damped is when the following formula is equal to 0. So when these constants from our equation equal to 0, it transitions the solution from overdamped to being critically damped. So to see how this affected the solution to our equation, we first looked at the general solution for the overdamped case, and then we defined this quantity epsilon and watched as it approached 0 what happened to this solution. So then our solutions will be of exponential form this time, because we realized the fish's mouth will open and close rapidly, meaning it returns to equilibrium quickly, which comes back to our definition for critically damped. And as this happens, the equation evolves into the form shown here. And then for some further simplification, we let C1 equal negative C2. Then we used the fact that when epsilon is small, the following Taylor approximation can be used so that e to the epsilon t is equivalent to 1 plus epsilon t. And this yields the following equation, u low, which y at t equals C1 t e to the negative et over 2m. And then we did some more simplification and found a general solution here. And finally, we used our initial condition again, showing that C1 must be 0 if our initial vertical displacement is to be 0. And this solution is more realistic because it encompasses the fact that the damping force does play a role in the movement of the jaw. And finally, if we've been given more initial conditions, such as the maximum y displacement of the jaw, the measurement of that distance corresponding to a specific time, we could further solve for C2 and find a unique solution.
So then we're going to talk a bit about our SCUDEM experience and what we thought we learned best from the experience. Personally, for me, I know this project challenged me to use knowledge from past physics classes and math courses, where I didn't think I'd use that information in the future for certain problems. But moving into this problem, I think it helped us use stuff from other classes that we didn't think we'd eventually use. And it also helped us gain experience working with groups of other individuals, where we all have different academic backgrounds. Personally, for me, as like an astronomy and astrophysics major, I tend to try to stay away from math, and I didn't really expect to be doing this, but I think it was a pretty good learning experience to challenge myself a bit and learn a bit more about how physics can be used in real life scenarios. And the final point I have here is that I gained research experience by reading through the source and extracting the information to develop this method for solving the problem. I think this, like analyzing the source really well, really helped us create a good model for the situation.
All right, and then for what was beneficial about my experience is, personally, this challenge was very different from previous projects and assignments I've done in school. I really liked how we had to use our problem-solving skills to solve the problem, but it wasn't like a step-by-step instruction problem you get for a homework assignment or simple projects in school. And I also enjoyed the collaboration aspect that SCUDEM gave us, and working with my teammates helped me better learn how to solve problems with others. Another point was we utilized LaTeX software to write our presentation, and gaining that skill has prompted me to use the software for other projects and assignments, and it's a really great skill to use to make professional presentations. And finally, practicing mathematical modeling in this setting is really great practice for future work in academics or in industry as a career.
And for my experience, this was actually my second time competing in SCUDEM. I had the ability to accept the challenge last year, which was really fun. Last year, my team also attempted the physics problem, but last year it was an attempt to model the movement of a bike when a contestant froze it at the end to gain advantage at the end of a race. But after that experience, I felt much more prepared this year, knowing what the judges would care about, what types of questions they would ask. I felt I had I was a little bit ahead in that and I could anticipate what they would be asking. And just like Emma, I loved the ability to practice problems that didn't have clear instructions to a solution. I will encounter stuff like this in my career or graduate programs that I go on into. And this problem tested my knowledge from when I took ODE and PE. And so we have some of our acknowledgements. We wanted to say thank you to our coach, Anthony, for encouraging us to accept the challenge and present today at this expo. And we wanted to thank the judges at SCUDEM for reviewing our presentation and giving us so much amazing feedback. And then Simeo for giving us the opportunity to complete this challenge and present today.
Thank you very much, Wilson. If you guys have any questions, we can take those now.
First of all, thank you, team. Wonderful job. What year are you in your careers at Florida Tech?
So I'm in my junior year, and I believe Emma is also in her junior year. We're in the same track for graduating, and then Emily, senior, she's graduating this semester.
Okay. And Emily, you did this last year, is that right?
Yes, yeah, I competed as a junior.
Okay. Do we have another question from someone? Then I'll ask the question, were you drawn to the sort of the physics nature of this as opposed to the maybe social science or life science immediately, or did you have to do a bit of wrangling to get your group to converge to this?
Yeah, so I feel like my background with astronomy and doing different physics classes and whatnot definitely drew me towards the physics problem immediately, because I already had that background with different models and physics scenarios and similar experience with like differential equations and whatnot. And I feel like all of us sort of came together on that because we realized like, oh, we can create a solution to this using our experience.
Yeah, Emily and I are both applied mathematics majors, but we both have our areas of like specialization for sciences in physics and space sciences. So again, we were just kind of drawn to that type of problem and thought we could apply our skills to it.
And did you learn anything about what fish could learn or what evolution should move to make the predator better with respect to motion of the jaw? I mean, is there some variable or notion that you saw that could be crucially improved? I'm not sure quite what I'm asking.
Yeah, I think I see like for when Emily talked about the like range of the feeding technique, one of the main things we realized it depended on was the like reaction time. So as the fish like opens its mouth and sucks in the prey, it needs to be able to close it fast enough without letting the prey escape. So that's kind of something like it needs to open and close quickly, but also still open enough to encompass the prey. So it's kind of a complicated scenario.
And
So just an interesting way to take the problem further, to analyze all aspects of it.
I think we could probably look at actually how much flow rate of water is going into the fish's mouth. So like a larger fish would have more water going in at a time. So that displacement of liquid would hold more fish in. For example, like a whale can consume like a lot more fish than a bass because the suction feeding technique encompasses a larger area.
And during the period you were working on this, which was 3 weeks, did any of you have any nightmares of large, monstrous things chopping at you?
Maybe nightmares of math, maybe not this.
Yeah, you're not getting it done on time, but
Okay.
yeah, it was definitely great.
And how many, you have a rough idea of how much time you committed to this in terms of over the 3-week period? How did it go? Less intense, more intense? How?
We definitely took a couple specific days where we met together and first like brainstormed and looked at the problems and decided what we were going to do. And then I think maybe we took like 2 more days of working for a long period of time. Like one day we sat down in the classroom and worked for probably like 6 or 7 hours, just creating everything, practicing, running through what we were going to say. So it definitely was like a good period of time, but we managed it well.
Okay. Well, again,
Like starting off the process, it takes a lot to get the ball rolling initially, but then once you have that model that you want to go with and you start getting into it and going through the process and answering your questions, I think everything sort of starts to fall together in that regard.
Well, again, thank you very much. I'm glad you shared your experience and your obvious enthusiasm and joy in doing this. So that's one way to say thank you.